Outline for today. We're going to talk about energy, free fall on the moon, and a little bit about angular momentum, which is chapter 5. We will have homework 10, probably activated sometime tomorrow morning, like last weekend. And down below here is the SI schedule, although I believe Maria canceled today's session. She'll have a session on Friday, though. A few announcements. And my announcements are basically about the talking PDF. So let's just review this. It's a PDF with animated sketching and with anybody narrating. The pen actually records what I write and what I speak. So I'm speaking into a little teeny microphone. Oh boy. Let me check this. Okay. All right, and here's what it looks like. This is what it looks like for the afternoon, for the W section. I did one for them as well. I want to show you how to view and listen to it. Now, we've already taken a look at the livescribe.com/player web application. It works really nicely. I want to show you how the Echo desktop application works as well. And the Echo Desktop it's an application for your computer, right? So you don't have to use the web for it. And here's the download page, and I'll put the link inside Web Courses if I haven't already. And there's a Windows and a Mac version, so that's good. When you download it and operate it for the first time, you'll see a library here of all the PDFs that you've got. Now, right now, you've just got one, a 2-page PDF. Well, most of you don't have it yet, but for this class, we only have one talking PDF of 2 pages. So, at any rate, you choose the one that you want, you click on it, okay, so like this one here, and it pops open this window, and you've already seen what that looks like. Now, let me enlarge this a little bit. When you actually click on the image, it'll start to play. And it looks like this. And you get a little player, let me enlarge this a little bit. You get a little player control over here on the left. So you can, turn up the volume and, play it again and whatnot, stop it. I guess you could put bookmarks in there as well. Anyways, it runs good, and I highly recommend it to you so that you can get really solid on those calculations that I thought were important on exam 1. Boy, I don't really have anybody's attention. See a lot of people looking at their phones. All right. It's up to you what you want to do. I'm going to talk about stress energy tensor now. This is a famous scientist in California, John Baez, mathematical physicist. And on the topic of energy, he wrote this. Well, he was talking about something called the stress energy tensor in relativity. Well, the stress energy tensor is a basic gadget throughout physics. Since we all want to know where energy and momentum are going, the transport of energy and momentum, and how much there is sitting around, right? But it's only in general relativity, Einstein's theory of general relativity, where the stress energy tensor is sitting proudly on the right side of an equation, telling space-time how to curve. That's what Einstein said. He said energy itself, mass and energy, will cause space-time to curve, just like the surface of the Earth. Did you know that the circumference of the Arctic Circle, up there in the land of the midnight sun, the Arctic Circle, that circumference is smaller than 2 pi times the radius of the Arctic Circle if you move along the surface of the Earth. Did you know that? It's true. the Arctic Circle. So if you walked, there's a lot of icebergs and stuff, so it's probably possible to walk the entire Arctic Circle all the way around the Earth. It's so many thousand miles. And then if you compare that to 2 pi times the radius, so from any point on the Arctic Circle straight north to the North Pole, that distance walking times 2 pi is greater than the actual walking distance around the Arctic Circle. And the reason for that is that the surface of Earth is curved. That's a sign of curvature, where the radius of a circle and the circumference of the circle disagree. It's not strictly 2 pi r. And that's what we mean by space-time. That's spatial curvature. Now, here's the equation that John Baez was talking about. Now, you're not going to have to calculate anything. It's tough for me to calculate stuff using this equation. It's called the Einstein field equation, sometimes called the Einstein field equations, plural. And all of relativity is encoded into this. The Einstein tensor, G subscript AB on the left, and then the stress energy tensor, capital T subscript AB on the right. That's what John Baez was saying, proudly on the right side. Those are the two things in this. And Einstein said that the source of curvature in space-time itself is energy, or stress energy, as encoded in the stress energy tensor. Now, stress energy tensor, T subscript AB. That's where you find all your forces and energy and stuff, or as my old PhD advisor used to say, all the smokestacks of nature, the nitty-gritty of nature. So all the wild nuclear forces, all the electromagnetic interatomic forces, gravitational forces, all the energy levels of the atom and stuff. If you are trying to do it in relativity, they're encoded over here. Right? So that's where all the wild and woolly forces of nature are. Now over here on the left side in the Einstein tensor, very polite, very elegant, all the curvature equations. And they're very tough. You have to get a physics degree, and you got to go to grad school and study a lot of math and a lot of physics before you can tackle this equation. But yeah, the way that it's separated, Einstein separated all the curvature equations on one side and all the smokestacks on the other side. Now, these two photographs are from the same part of the world, Japan. On the left, a beautiful, elegant Japanese garden, all measured out, carefully tended, very precise, the way they do over there in Japan. But in other parts of Japan, a bunch of industry, smokestacks, blazing away. Okay, so that's where the nitty-gritty of nature is. Now, so this is kind of a colloquial picture of what, where energy shows up in the theory of relativity, all right, which is our modern theory of the gravitational interaction, which we've been talking about. Now, I want to relate this to Sir Isaac Newton. So here's the Einstein field equation. And the way that Sir Isaac Newton might make sense of it is by saying, oh yeah, my F equals ma. All I got to do is reverse it left to right. The curvature of space-time would partner up with the ma side of F equals ma. And all the smokestacks are over there on the F side, the force side. Okay. Now Einstein's field equation it's written in terms of energies and momentum. Sir Isaac Newton's is written in terms of accelerations and forces. Right? But the interesting thing is, and I rewrote this ma equals F specifically so that I could tell you that Where Sir Isaac Newton thought of acceleration, Einstein said, let's think of that motion not as accelerated, but as a result of the curvature of space-time itself. Right? And so Einstein said, let's encode curvature of space-time over here. Let me get my cursor over here on the left. And Isaac Newton said, all right, I'm going to encode my accelerations and stuff over here on the left. And my smokestacks are on the right, and I'm going to call them forces. And we're going to measure them in newtons. I'm going to name it after myself. I'm going to make sure somebody names it after me. And then over here, Einstein said, yeah, okay, my smokestacks are over here, but I'm not going to do forces per se. I'm going to do energies and momentum. All right, so energy. You know, there's one more person I want to tell you about with his comments about energy, and that's somebody called Richard Feynman. And he's a very smart guy currently. Well, he died a few years ago. And very smart guy. And I've studied a lot of his writings and stuff too, his theories. He was big in quantum mechanics. And so we'll probably talk about him a little bit later in the semester. He had some very interesting things to say about energy. Now, you're not going to have to worry about calculating with the Einstein field equations. By the way, those two subscripts, A and B, the A stands for 4 dimensions. You know, so it could be time. A would stand for time, X, Y, or Z. And B, same thing, time, T, X, Y, and Z. So there's 16 equations here. It's pretty bodacious. Very tough to work with. But it's a good theory, just like Sir Isaac Newton's theory is really good. And they're consistent with each other. All right, I want to do a workout using your iClickers. Get them out. Get your clicker out. Get your calculator out. And we're going to do some questions together. And instead of all this egghead talk about Einstein and, you know, John Baez. John Baez is a fantastic professor and a fantastic writer. I try to read as much as I can of his stuff. We're going to be a little simpler. We're going to talk about a hammer from Home Depot on the moon. And nobody here has been to the moon, I don't think. But we do know that the moon has a little bit smaller value for the surface acceleration. On the moon, g is equal to negative 1.62 meters per second squared, approximately. All right, so g subscript m, that's the g surface acceleration for the moon. And why is that? Well, the moon's a little bit smaller. Mass is smaller. It's about 0.0123 of Earth's mass. So that's about 1% of the moon is pretty small, I mean, compared to the Earth. I mean, it looks big up there, you know, especially when it's just rising above the horizon. But, you know, and the radius is about 0.2725 of Earth's radius. So that's a little bit more than a fourth of the size of Earth. So it's a good size, but I mean, it's pretty puny. So the surface gravity is not as strong. Right? Now, the hammer that we're going to work with, go ahead and write this down too. I just chose a random hammer at HomeDepot.com. There's a picture of it. What do you call this? A steel hammer with a fiberglass grip, 0.703 kilograms. All right, now, we're going to do some workout with work, but before we calculate work, we got to calculate the weight force. All right, take a minute to calculate the weight force, if you will. Turn the lights on full, please. So just take a minute to calculate that. And let me apologize also now while you guys are working, you can listen to me in the background. I should have, I know a few of you came all the way up to campus for class and did not realize that I had canceled lecture. I should have put something in web courses earlier in the morning and I didn't. I apologize for that. I'll try. Hopefully I won't have any more absences from illness or any other reason. But if I do, I'll talk to Miss Darian, I'll talk to Miss Caroline, and I'll leave something so you don't have to drive all the way in from Osceola County or wherever it is that you come from if there's no lecture. Weight force on the hammer, W equals mg. And again, let me caution you, do not mess up the symbols. Capital W in this context is weight force. But in the next slide, we're going to calculate some work. Actually, we're going to work with work and kinetic energy and stuff. So in that context, W is W for work. Okay, 30 seconds. Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go. Looks like you guys did good. Correct answer, ching, negative 1.14. So that's good. Okay, hit your refresh key because we're going to do a numeric calculation now. So you have to hit the refresh key. Before we do that, let me just review the strategy. For any kind of a free fall situation, whether you're on the moon or the Earth or some exoplanet orbiting another star, once you set the baseline elevation, okay, the surface of the moon, for instance, you can calculate the GPE at any height, the gravitational potential energy. All right? Then if you know the kinetic energy at any level, for instance, at the top of the motion, so in other words, if you're holding the hammer at a certain height and you drop it, okay, then you know at that height, kinetic energy is 0. So if you know the kinetic energy is 0 and you know the height, ching, you can calculate everything. Maybe you know the kinetic energy at the bottom of the motion. You know, you have some kind of way to measure kinetic energy. Or any other intermediate height. If you can figure that out, then you can calculate total energy E, the total mechanical energy. Right? And it's neglecting any kind of frictional forces. And you know what? There's no atmosphere on the moon at all. And so there's no air resistance on the moon at all. And once you have E, you can figure out the dynamical state completely at any other level that you please for the motion that you've got. So, in other words, you can figure out the GPE value at any height. You know, once you get it one place, you can get it any place else. Kinetic energy, the speed, you can figure that out too. We did that. Okay? So you did some of that for homework as well. All right, so that's our basic strategy. Let me pause for questions. Yes, Danielle. How did I get the what? The previous answer? This one? mg. Okay, the mass was 0.703 and the g is negative 1.62. So negative 1.62 times 0.703 gets you 1.14 newtons. Okay. Now on Earth, that would be about 7 newtons of weight force. So it's a little bit smaller up on the moon. Okay, so here's the strategy that we just went through. And yeah, you could do this. And you guys, we're actually going to do this again when we study atoms, because the energy levels for an atom are really important. But those are all electrical, so it's going to be electrical potential energy that is important for them. All right, here's your problem. And just take a minute to calculate this. The astronaut drops the hammer, same one, 0.703 kilograms, from the small platform of the lunar module, from a height 2.2 meters above the surface of the moon. Okay? What is its kinetic energy halfway down at height 1.1 meter? Type in the numeric part of your answer to the nearest 0.01 joule of kinetic energy. And actually, this is a really easy one if you think. But if you do it the long way, it's not too bad. So give it a shot. Okay, can you turn all on now? Yeah, I just want them to see it for a little bit there. Okay. What are you studying?
I'm not studying.
You're not?
No, not currently.
Oh, okay.
I'm scheduling currently.
Oh, okay. Busy? Yeah, okay. Yeah. I guess. I don't have a schedule, but I just do the things I'm supposed to do. They go where they tell me. But hey, you guys, is it ever possible to have a negative number for kinetic energy? No, because v squared is always going to be a positive number. Mass is always positive, so if you have a negative number for your answer, you're automatically, and I can see one person with a negative number. You out of here. All right, and round off carefully. Aha. Correct answers. Clicking away. Sweet. I still see negative. Oh, there's an error. Oh, somebody changed their number. Somebody had the right answer and then they changed it.
That's unfortunate.
Huh?
That's unfortunate.
Yeah.
They changed it up. No.
No, it's just the percentage now.
No, it went back up to 18 and now it's back down.
Okay, now it's okay. There we go. Good, good, good. Yeah, work carefully. $19. $3.18. $90 seconds. Two weeks from today, we have exam 2. 3 weeks from today, we have spring break. Yes.
I'm ready. I'm so ready.
I've been ready for spring break since January 10th. What are you talking about? Why can't they schedule spring break right after Christmas break? No. It would be nice, but do they do that? No. Okay. 30 seconds. By the way, students, this is the 14th lecture. Halfway point. We have 28 lectures for the full semester to the end of April. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. No, just keep it there. The answer is 1.25 to 3 decimal points, 1.253. You know what you could do? The easy way to do this, your total height is 2.2. The halfway point is 1.1. So if you figure the GPE at 2.2, 2.2 times 1.14, then half of that is the potential energy and the kinetic energy value at 1.1. So all you got to do is divide that by 2. You know what, Kane, as I just said, there's a bunch of different ways to look at it. Now, if I gave you, some other point that wasn't halfway, then you just have to do, GPE and the... Yeah, at halfway, the GPE, at, half your, if you drop it, at the halfway point, you're half kinetic, half potential. If I'd given you 1.0 meters or 1.74 or something like that, then you'd have had to calculate everything out. But at the halfway point, yeah, it's 50-50. Side note, you can write this down. The speed, downward speed, is 1.8. Sneezed and this thing stopped the podcast. All right, here we go again. So yeah, the downward speed is 1.89. And I'll leave that for you. You can verify that later as a study exercise if you feel like. Keep it ready for the final, or just do it tonight or something like that. Question? Yeah, mgy. Minus mgy. And the mass you have is 0.703 kilograms. Okay? But g is negative 1.62, remember? What is your name again? Maya? Maya, the g is negative 1.62. Right, so 1.1 times negative 1.62 times 0.73 kilograms times the minus sign is positive 1.253, and that's the same, at the halfway point, that's the same as the kinetic energy. Okay. Now, I want to keep going and ask you some more clicker questions. Hit the refresh key. We're going to do some multiple choice. And I'm going to ask you some questions about centripetal acceleration, and you're visually going to make a decision or an analysis concerning the velocity and so forth, the acceleration of a car, of people driving down a track. Okay, and the reason we're going to do that is because I want you to start thinking about curved trajectories and angular momentum. That's our big topic for Chapter 5. So, question number 3 for today. Multiple choice, test driver X. Both turns, turn 1 and turn 2, at 88 miles an hour. Think. I see, I hear pages turning. People looking in their notes. Very good. What's that formula for centripetal acceleration? What over what? All right. You guys are doing good. That's interesting. 30 seconds. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Click. All right, go ahead and display that. All right. Now, this one we got a spread in the answers. Let's talk about it. And just so you know, we're not going to stop talking about F equals ma and weight force and centripetal stuff till the end of the semester. I mean, once we've established it, Elizabeth, and that we're going to keep talking about it. We're going to be talking about energy all the way, momentum all the way. I mean, we're just going to be, so this takes us back a couple weeks. But here's the correct answer. The majority of you, 52%, did vote for that. And here's why. The turning radius for turn 2 is smaller. And the turning radius for turn 1, it's a very gradual turn, so it's got a much bigger turning radius. Okay? And actually, those are kind of imprecise, but they're fairly close. Those are representative. Turn 1 is a bigger turning radius. And for that reason, v squared over r, he's got 2 accelerations. V squared over r, v squared is 88 miles per hour squared for both accelerations in the numerator. But the denominators are different. V squared over r, r2 is smaller than r1. Small denominator, big acceleration, big quotient. All right, so that's why turn 2 is the correct one. Another way to think about it is in terms of more colloquial terms, not using the equation. If you think about it, if he's got bad, like bald tires on his race car, which turn is he going to be more likely to skid out or, go into a four-wheel drift? Turn 2, because it's a tighter turn. Okay? He needs more grip. He needs more friction force to give him more friction centripetal acceleration. He's not getting it. He spins out. Question number 4. Scaredy cat Joe. Okay, this little kitty cat is going to run the same track at 4 meters per second. It's about 9 miles an hour. Now read and think carefully. I saw this video on YouTube the other day of cats getting startled. Apparently cats, they have a tendency to jump straight up in the air when they're... Now, how is that an evolutionary advantage? To jump are cats just morons or what?
I'll just jump over the predator, I guess.
Oh,
Can't kill what you can't catch.
I guess, yeah. Well, that would be a good trick. you know, the tiger's coming at you, you jump straight up in the air. Yeah, good. Okay. All right. That makes sense. All right. Clever. A clever revolutionary advantage. All right. All right. 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Most of you got this one right. It's less than. And for those of you that didn't, here's why. The V is smaller. The numerator, smaller. R is the same. So they're both going through turn 1, right? So same radius in the denominator, but now the V is smaller for the kitty cat, so his acceleration is less for Scaredy Cat Joe. Now, I've been asking about centripetal acceleration because we want to look at orbits. We're going to look at orbits a little bit more, and we've already talked about them a little bit. So let's do a little recap. We know from Newton's 3 laws, centripetal acceleration and universal gravitation, that there's a simplification of the forces and accelerations for orbital speed v and central mass m, the orbital size r. You have a fairly simple equation, gm over r equals v squared. Now the central mass, if you're talking about a spacecraft orbiting Earth, capital M would be the mass of the Earth. If you're talking about a planet orbiting the sun, then capital M would be the mass of the sun. If you're talking about the rings of Saturn, then capital M would be the mass of Saturn. Matter of fact, this is actually one way that we figure out the mass of Jupiter and Saturn and stuff by timing their satellites, their moons, timing the rings. Stuff like that, and you can figure out capital M. Now, on circular orbits, we have this fairly simple expression for the orbital speed. 2 pi r, the circumference, divided by the period of the orbit, capital T. Right now, we talked about that before. Fairly simple. If you have an elliptical orbit, it's a little trickier, because on an elliptical orbit, at apogee, far away, at the far end of the ellipse, you're fairly far away, so you're just kind of poking along. At perigee, down close, you're really cooking. Right? I'll show you a picture of that in just a minute. But for circular orbits, it's fairly simple. And here's an example. A spy satellite, you want to look at the Russians. You specify the r that you need, and from that you compute the orbital speed. Okay, so altitude, let's say your cameras are good out to about 180 miles. Okay, if you're 180 miles away, you can read what's in Boris, or what's that guy's name? Vladimir Putin's. You can read what's in his back pocket. And so you know that you have to give your rocket a speed. You use that to figure out v squared and then v. All right? Another thing is the geosynchronous communication satellite. So for that, you specify the orbital period and then compute r from that. Now, specifying the orbital period implicitly forces you to take a speed. So for a 24-hour orbital period for geosynchronous communication, in other words, they stay right above a certain point, above the equator of the Earth. Like for us, it's things over Brazil, somewhere over the Amazon. 6,900 miles per hour. So the rocket has to boost you up to a certain distance, 4,200 kilometers, and all the way, or altitude 42,200 kilometers radius, altitude 35,900. And that's about 6.62 Earth radii away from the center of Earth. So That's out there quite a ways. All right, now we already talked about that. And for the important factors in all of this is to specify the orbital energy and the orbital angular momentum. And from that, you can figure out all the other specs for your orbit. Okay, so for low Earth orbit or high eccentricity orbits, LEO is low Earth orbit. So that's where, so something like the space shuttle, that's about where it is. I mean, if you know, I did these proportions pretty carefully. The space shuttle, the Hubble Space Telescope, they're down there in that little dashed line right around the Earth there, where it says LEO, low Earth orbit, space station. Now, a spy satellite might be a little bit different. What they like to do is get down close, so they might, and then, you know, loiter on the other side of the Earth. So this one might be like the elliptical orbit for a spy satellite looking down on Russia, right? So when they're down here, when they're on the side of the Earth where Russia is down here in the lower right of this picture of the Earth, they're going by pretty fast because they're at perigee. Excuse me, yeah, they're at perigee. So they're whipping past there really fast, but they're low, and that's what they, you know, they need. Now, when they're over here, the other side of the Earth, you know, they might be flying over Australia or something like that. So they don't really care too much about that. They're out there, you know, and out there at apogee on the highly elliptical orbit or high eccentricity orbit, they're kind of poking along out here at apogee. That's all right. They're flying over Australia. So there's just a bunch of kangaroos and sheep and stuff like that. A bunch of guys. Ooh, some really deadly snakes. Stuff like that down there in Australia. So maybe it's better that they stay high altitude. And then, of course, geosynchronous is out here. You know, so the orbital state is described by energy and angular momentum. That's it. Right? And so let's talk about angular momentum. Angular momentum is a special kind of momentum. It's constructed from mv, regular linear momentum we call it, or translational momentum. P equals mv. But it's associated with something that's either spinning or moving past an object or moving around an object. And so an ice skater, if you've ever seen an ice skater, you know, they start spinning with their arms out. And then when they bring their arms in, they really start to spin like crazy. And if they're already spinning like crazy and they want to stop, they spread their arms out. And this ice skater here has got her, notice she's got her legs and her arms out. And that is why, and you can tell that she's trying to slow down a little bit. And she's trying to, you know, look graceful and all that stuff. Now, so the ice skater effect, ice skater momentum, the spin angular momentum. Another thing, here's a bicycle wheel. And think about a bicycle wheel spinning on its axle. Okay? Each centimeter of the tire, you can think of it as like a pixel of mass. And it has a distance from the center. Now, if you've ever noticed, a big wheel is sometimes easier to turn than a small wheel. All right? And so the grams of mass and every gram of mass on the wheel, on the edge of the wheel, and every part of the wheel, really, the spokes too, has some meters per second of speed. And if it's a wheel, it's going in circular motion, so the velocity is perpendicular to the position. So the velocity vector is perpendicular to all the radial, well, the spokes aren't radial though. They're kind of offset a little bit. But they're all perpendicular. They're tangent to the circle and perpendicular to the radii, and the spokes are almost radial, but not quite. Okay, so there is momentum for each pixel. So if you pixelate the bike tire, you can pixelate, think about it, the ice skater. Any irregular object, if you pixelate it, and then figure out location, mass, and speed, you can figure out angular momentum. All right? All of it is oriented to the axle. And the wheel is spinning. It might not even be moving from point A to point B. All right? But we still consider it to have momentum. You know, it might be that you have your bike tilted upside down in your garage. You know, you have it balanced on the handlebars in the bicycle seat. And you're working on the gears or something. And the wheels are going around. And they're not going, you know, from point A to point B. But they have MV. Each atom in the bicycle wheel has some MV and has some mass. And therefore, it has some momentum. Okay? And angular momentum is how we... Now, reading in chapter 5 is where you want to look more deeply into that. So this is kind of giving you some tips to read in chapter 5. Another thing in chapter 5 is that angular momentum is a conserved quantity. Now, think of the ice skater effect. I already mentioned that to you. When the ice skater brings their arms in, you know, they've redistributed their mass, okay, and they've changed their dynamical state, their spin state. They're spinning faster. If they extend their arms out, they'll slow down. And I think Tuesday I'll bring in some demonstrations of angular momentum that are kind of cool. And we'll have some volunteers from the audience. Okay. Now, angular momentum is a conserved quantity. So these ice skaters, they have, their skates are designed, and the ice has to be pretty hard, and their skates have to be pretty hard, very smooth, so there's not much friction. But they have to be sharp, because that's how they get, you know, they get traction. They get moving from point A to point B by using the edge of their skates. But if they're on the surface of their skate, it's pretty smooth, not much friction. So angular momentum for an ice skater, you know, eventually they'll slow down, but if they push their arms out, they'll slow down quite noticeably. Okay? Here's another picture. I want you to look at this. This is an overhead view of a crescent wrench that's been spun across a tabletop. And if you look carefully at this image, you'll see a darkened in plus sign. And I'll put my cursor here on this one. All right? And if you additionally study very carefully, you'll see that the plus sign is moving in a straight line. Now the wrench is spinning around that plus sign. Students, that plus sign, that darkened in plus sign, is the center of mass for this wrench. Okay? So if you throw a wrench so that it's going to spin, the center of mass will act like a particle. It'll act like a baseball. But if it's an extended object like a wrench, it'll spin. I mean, if you throw it right, it'll spin. Okay? If you just drop it, it won't spin. But this one's spinning. Now, I made some blue, kind of light blue diamonds here, and these are spaced out exactly above those black darkened in plus signs. Okay, so here's a good one. Now, see I've got those covering? Let me go back to that. All right, here are the diamonds. Let me move them in. Take a look at this. Not your phone. Take a look at this. Okay, there they are. All right. And what that means is, if you look at those blue diamonds, they look like they're constant velocity. All right. But it's still spinning. So there's a huge set of momentum states when you look at atom by atom, pixel by pixel, gram by gram. But if you just look at the center of motion, piece of cake, a walk in the park. Right, here's another. So angular momentum is conserved here. It keeps spinning. Now here's another one where I don't even want to think about this. I mean, you might get an upset stomach just looking at it, this guy. Can you believe that? I don't know. What is that, a backflip? No, it's a front flip. Oh, man. I just, you have to be really brave to do that. Here's another. But, when he's in the air, he just keeps spinning. But then as soon as he hits the ground, he stops because the ground is rigid and it'll prevent it from spinning. Okay? And here's another one. Now this one's kind of cool. Look at this one. It's very symmetric. Okay? Now look at this guy over here. Okay? He's coming off the ramp over here on the far right. Okay? He's looking up and ahead. Right? Now over here at the very top, he's upright. All right? You see that? And then by the time he gets down here, right down here, he's looking down and ahead. Right? So it's a good spin. He's timed it just right. Right? And in motion, up in the air, angular momentum is conserved. Here's another system where angular momentum is conserved, something that was in the news yesterday. The exoplanets around that star, TRAPPIST-1. Here it is. Here's an artist's conception. This is from the NASA website. And yeah, you can read about it in Nature, the journal Nature. These 7 alien worlds could help explain how planets form by Alexandra Witz. That was yesterday. And I'll put the link to this in web courses a little bit later tonight. Yeah, 7 planets. Now, let me emphasize to you here, we don't know what color the planets are. So artist's conception, yeah, definitely put quotation marks around that. It's more like artist's fantasy. Like planet G here, we don't know that it's green. And planet B, we don't know that it's orange. And look at planet F over here. Looks like it's got oceans and continents and stuff. We don't know jack about that. All right? But we do know that there's 7. And 3 of them apparently are just the right distance, we think, from this star. It's not a very bright star. And they're just the right distance that we think that liquid water could exist on the surface and form lakes and rivers and oceans and stuff, if there is any water. Now, you can bet your bottom dollar they're looking very hard for water. Now, here's the actual data. This is not the artist's conception. This is the scientific observational data. I'll explain it in a minute. This is from another article. This is the actual technical article by Michael Guillaume et al. And it's published today. 7 temperate terrestrial planets found around the nearby ultra-cool dwarf star TRAPPIST-1. So it's a pretty small star. It's red. It's not as hot as the sun. But these guys are in close, too, so they get enough sunlight that maybe they can support life. Now, in this lower left, you can see that this is a record of the brightness of the star, and they've got all 7 planets stacked up here in one graph. So what they do is they take, an observation of the brightness, like every 20 minutes, or every 2 days or something like that. And when they notice the brightness dims, that's when these curves dip downwards. So if you look at this top one here in graph C on the left bottom, the top one, it's pretty bright up here, and then it dips downward. And that's when the planet is in front of the star. It's an eclipse. It's blotting out just a small fraction of the brightness of this star, but we can pick it up, right? And we've measured it. These are measurements. This is not artist's conception. These are measurements. And then a little bit later, it dips back upwards to its normal, and that means that the planets moved out from in front of the star. Okay, and we can see 7 of them. So this particular star has got 7. Now, here's what they think the star system looks like. Look at that. Right here in the middle, yep, that's the star, TRAPPIST-1. And around it, they think, are these 7 exoplanets. So yeah, angular momentum. It's a definite conserved quantity in star systems, bicycle wheels, daredevils on motorcycles, and all kinds of different systems. Question? The dotted and dashed lines, I'm not sure. I believe that's probably what they call the habitable zone. In other words, the zone where you're far enough away that but not so far. You're far enough away that water is not going to be steam. It's going to be liquid. And not so far away that water is going to be all ice. Okay, so that's the outer ring. I think. That's my guess. I didn't think to look that up, but I'm sure, I'll post these links in web courses tonight. You can go look it up. Yeah. It's pretty interesting. Anyway, now, a couple other things I want to point out to you in your effort to study Chapter 5. There are some lovely YouTubes showing angular momentum. And just go to the playlist, the list of playlists. And one of them is dedicated to angular momentum. And Darian and Caroline are in this very first one. Okay, that's from a couple semesters ago. And I think on Tuesday next week, I'll bring the same equipment that you see in those videos. I'll bring them here to lecture. And we'll see if you guys can enjoy angular momentum demonstrations. Now, here's a couple more questions to go over. What is it that changes the angular momentum state? This is a diagram from Chapter 5. A force, a net force, will change the momentum state of an object. F delta t equals delta p, we know that. But what about angular momentum? Well, when you apply a force on an extended object, like this board floating in a lake, from page 74 and so forth, it doesn't act the same way baseballs do. Because baseballs we treat as a point particle. They're symmetric and they're rigid, and we just treat them as a dot in space. But a real object like a board can have a complex trajectory. So, for instance, depending on the amount of force, F equals ma, and the amount of torque that you put on the board, you're going to get different motions. So, for instance, when I say different torque, F1, if you push along F1 with a certain number of newtons, and the center of mass is point C, then that board is just going to accelerate upward in this view. All right? It's not going to spin. If you exert a force out here through point A, which is a certain number of centimeters away from point C, then you're going to give it some newtons of upward acceleration in this view, and you're going to give it some torque. You're going to cause it to spin. What direction is this one going to spin? Clockwise or counterclockwise? Clockwise. All right. So your torque on this is going to be clockwise. If you apply the same force to the other side, the right side, you're going to cause counterclockwise spin. And so your torque is counterclockwise. Now, some boards are easier to spin than others. All right? Some objects in general are easy to spin. How do you quantify that? You use something called the moment of inertia. The moment of inertia is what encodes the ease or difficulty of spinning up an extended object. Now, an extended object, this is a little more complex than just measuring the number of kilograms. King.
Going back to the last slide,
This one?
yeah,
Yeah, B is out here. So this is a diagram from the book, and I believe my sentence in the book said from A directly towards B. So that's in the book. This diagram's right from the book. All right? Okay. Ease or difficulty of spinning up an object. So like these two barbells, the one that's going to be easier to spin up is the one with the barbells in close, 45 centimeters apart. The one that's going to be tougher, Bobby, is the one that's got the two weights 60 centimeters apart. All right? And so even though the masses are the same, the arrangement of the masses is going to be different. And this is why ice skaters find that when they extend their weight, even the weight of their arm outward, it slows them down. They become harder to spin. When they bring their arms in, it's easy for them to spin, and so their spin rate increases. All right? Now, the moment of inertia, it's a very abstract definition, but it's basically this. Take every pixel of mass, no matter if you have a symmetric object or a complex oblong object. Just think of every pixel and take your center of mass and measure the distance from the center of mass out to that pixel. That's R. And then square it. And then multiply by the number of kilograms or grams in your pixel. And that's mr squared for that pixel. And then do it for every other pixel in your object. And that's going to be the moment of inertia. Now, the angular momentum is then going to be capital L. It's going to be equal to the moment of inertia, the sum of all your mr squareds, times omega. And omega is the symbol for angular velocity. Now, angular velocity, as you'll read in the textbook, is expressed in, for instance, colloquially, RPM. And back when I was a kid, we used to listen to records on the record player. And they had, the really old records were 78 RPM. And you put them on this little thing called a turntable, and they spin around. You can see it on the internet and YouTube and stuff, records. Some people still have them. I remember them from when I was a little kid. So RPM, degrees per second. There's a zillion different ways to express omega, the angular velocity or the angular speed. Question?
I thought I got what you were saying. You were saying pixels, but I'm a little confused as to what exactly you mean by
Yeah, you know what pixels are for a picture, right?
like when it gets little.
Yeah. So if you think of any object in the world as divided up into little cubes, I mean mentally, or here's another thing. If you go to the movies and you watch a scary monster movie, they have monsters from outer space or zombies or something like that. A lot of that's computer graphics, right? And so what they do is they tell the programmer, okay, I want, a zillion, 2,000 pixels here, and they all got to be red. And 13,000 pixels here, and they all have to be green. And then they animate each pixel. And that's why computer graphics takes so much computing power. They got to animate. Can you imagine? I was watching the Transformers movie once, and I was thinking, why did they make the Transformers so complex? Everything, if you ever noticed that on Transformers, everything's spinning. And what's the evolutionary advantage in that? If you're a Transformer and you're ready to, if you're trying to do battle with, evil robots, how does it, they have a zillion parts that, excuse me, they have a zillion parts that can go wrong. It can break and stuff. I always think, these things are not made for battle. They're made for thrilling little 6-year-old boys or something like that, I guess. But anyways, those complex Transformers, and then they are all animated by computers, pixel by pixel. And believe me, they do enormous amount of computation. And then they change the shape of it. And all that's, computer generated too. But they have to take a list of all the pixels and just, and that's what we're doing here. We're taking all the pixels and computing mr squared for each one and then adding them all together. And if you have a lot of big r squareds, it's going to be hard to spin. If you don't have many mr squared, if you don't have many r squareds, if you're in here, it's easy to spin. Okay, so your assignment for the weekend is finish reading chapter 5, read ahead into chapter 6, and homework number 10 on all this today will be ready tomorrow morning, maybe earlier, due on Tuesday. You are dismissed. God bless you.